Hello, my name is Cory Rupp. I'm from ATA Engineering, and I'll be talking today about a Modelica library that we've been putting together to analyze rotorcraft. Specifically, this library is tailored for analyzing the aerodynamics of rotorcraft and a specific application to Whirl flutter. Our motivation for developing this library comes from emerging rotorcraft, specifically eVTOL vehicles, electric vertical takeoff and landing vehicles that really tightly couple a lot of physical phenomena or physical domains together, more so than a traditional rotorcraft would, which already does this, already couples a lot of things together. Added to the traditional aerodynamics, rotor mechanics, and dynamics and power systems are the electric rotor dynamics, the electric power system, and then the control system of that, as well as many independent rotors that may be powering the vehicle not only in vertical lift, but also in forward propulsion, sometimes at the same time. So this problem is quite difficult. And so what makes this difficult, in fact, more difficult than a traditional rotorcraft problem? One reason is there are multiple interacting rotor wakes. These vehicles tend to have a lot more rotors than a traditional rotorcraft, which may have one in the case of a helicopter, sometimes two in a helicopter, and then in a forward flight aircraft, might have two or four, but these are generally widely spaced. In the case of eVTOL, they're much more closely spaced, and so the aerodynamics problem gets more complex because of that. The fact that these rotors are variable RPM is also a complicating factor. Traditional rotorcraft are designed for constant RPM. This is usually due to power optimization or engine constraints. And then usually the aircraft structure is designed around these operating conditions. In the case of variable RPM, it's much more difficult to design your structure and your aircraft around these different operating modes that will be changing throughout the course of the vehicle's flight. The electric rotors, again, add a complication because now you have a power supply, thermal, and efficiency considerations that you have to wrap into everything. The independent rotors introduce a different trim problem that is under-constrained because you tend to have more rotors than degrees of freedom that you're trying to control. And one of the reasons that we're developing this tool, or this library, Modelica library, is because we found that a lot of existing analysis tools for rotorcraft are insufficient. These are usually tailored designed for rotorcraft with a fixed RPM and very few rotors. And so looking at these eVTOL problems becomes difficult to impossible for existing tools, and extending those tools is generally prohibitively difficult as well. Also, coupling in the electrical system to these tools presents a difficulty in addition to the variable RPM behavior. So we developed a tool or the library to tackle this problem. Many of the components of a rotorcraft, in particular eVTOL systems, can be already analyzed using the MSL, the Modelica standard library. The multi-biodynamics of the rotors, the mechanisms that control the rotors, and the different hub topologies and all the different things that can be present there. The electric motors and power systems can be modeled already, and the control systems can be modeled. However, the aerodynamics is not something that's currently available in the standard library or in a lot of places. So we developed this to kind of bridge that gap. This library that we developed is called the Rotorcraft Aerodynamics Library, or RotoAeroLib for short. And again, it's targeted toward the aerodynamics of the rotor rather than all the different pieces. It complements the multi-bio library, of course, in which the main connector The main interface is the frame connector. It contains a number of specialized blocks, in particular the air station, which is for modeling the aerodynamics and transferring the aerodynamic forces to the blade. Also included in the library are models for the rotor blade, an assembly of blades, and then the rotor itself, which interfaces all the different control components, including the swash plate or linkages, and how those connect to the blades. The blade itself makes use of the open source deploy struct lib, which is another library we've developed. And this is mainly to enable using flexible blades for these rotor analyses. Also in the library are some examples that show how to set up these problems. The aerodynamics of the blade are contained with the air station model. This model, in its basic form, implements blade element theory, also called strip theory in the field. The air station is attached to the airfoil, the blade, in the airfoil coordinate system. And it also references the rotor reference coordinate system, and it does this between these two coordinate systems as the blade moves around, as it rotates and flaps and feathers. You can, between all these movements, you can calculate the collective, the angle of attack, and all the various geometries that are relevant for this problem. Multiple air stations are generally used to span the length of the blade, and this is typical of all rotorcraft modeling tools. And this is to capture the varying airflow speeds as you go along the length of the blade. The tip, of course, being moving through the air much faster than at the base. Lift coefficients are currently limited to a quadratic function of the angle of attack, but this can easily be extended in the future to use a table if we wanted. In general, the basic form of the air station is sets up all the transferring of the basic fluidic forces into the frame of the blade and facilitates the transferring of those forces. However, if we want to do something more complex, such as blade element momentum theory, we have to add correction factors. And so a number of different correction factors are supported. Corrections for inflow, for example, Mach number. So you can imagine the tips of the blade obviously move a lot faster than the inner radius of the blade. And of course, there could be Mach number effects happening out there. Also tip loss effects due to rollover at the tip of the blade. So a lot of these things get applied to different parameters in the model. And one thing to note is some of these, including the unsteady aerodynamics, can drastically increase computational cost of solving the problem. You can see in the non-circulatory unsteady aerodynamics that there are first and second derivatives of the state variables for the rotor air station, and this significantly complicates the problem. Here's a simple example of a quadcopter using the rotor aerolib. So each one of the rotor blades, or each one of the rotors and each one of the blades has these air stations connected to it. And so together they introduce a thrust into the rotor, and those rotors together introduce a thrust onto the body of the quadcopter. This model is controlled through the voltage of the electric motors that are connected to the rotors. And you can see as we change the altitude set point for the control system, you can see the change in the control voltage and ultimately the motor speed that we see in the rotors. So the main thing, one of the main reasons we wanted to use this tool was to look at Whirl flutter. And what Whirl flutter is it's an aeroelastic instability that's exploiting the coupling between the aircraft structural dynamics, so the flexibility of the wing, the rotor gyroscopic forces, and then the rotor aerodynamics themselves. Initial studies were performed in the 60s by a number of different people, and these were driven by some incidents with the Lockheed Electra aircraft. On the right, you can see a mock-up of that aircraft before the test and after the test with a wing missing. And on the left movie, you can see some of the, or you can see when whirl flutter happens. And so there's a rubber band attached to this rotor that's in an airflow wind tunnel, and it's stable in this case. And then once the stiffness of the spring is lowered, it enters a critical regime where it's no longer as stable. And so these effects, of course, directly impact the flight envelope. So we built up a model of the Bland and Bennett propeller, which is, they did some, Bland and Bennett did some experiments early on to look into these studies, or into this effect, trying to find the flutter boundary. And so this is kind of what that looks like. Things to note are the blade, or the rotor is in free stream velocity and is free to rotate without drag or propulsion being forces on the rotation of the rotor. And then at the base of the pylon, there are two joints for pitch and yaw that have a stiffness and damping to them that represent the stiffness and damping of the wing. You can see the actual test article that they used in the pictures below. And so they did this study varying the free stream velocity and looking at different damping parameters, keeping the stiffness of the pitch and yaw motion or springs constant, but changing the damping value, since damping is the primary thing that influences stability. And they also looked at several different pitch angles for the blades. So looking at, in our comparisons to this data set, our Modelica model started with an initialization problem where we set the set the free stream velocity and solved for the rotor speed and balanced all the aerodynamic forces and everything. And then we linearized that problem at time equals 0, extracted the eigenvalues of that linearization, and then determined from those eigenvalues, if it had a positive whirl part, then it was an unstable system. If it had a negative whirl part, then it was a stable system. And from that, we could find, through a parameter study, the flutter boundary for the rotor. And so we varied two different things. We varied the damping of the springs at the base of the pylon, essentially the damping of the wing, the modal damping, and then also varied the free stream velocity of the airflow. And these can be combined to reduce into reduced quantities for the reduced velocity of the airflow, as well as the structural damping, overall structural damping of the wing. So here's some results that from these studies. You can see a good correlation between our model and another an analytical model called Hobart-Reed theory, which is the dashed line in these examples. The blue dots and the red X's nicely straddle this line. Also shown are the black dots, which are the, of course, being experiments, sparsely populated flutter boundary from measurements. And of course, we don't capture all the effects, so it's not, but what we do show is that we are conservative here. And we are closely replicating the Hobart-Reed theory, which is good, despite having slightly different formulations. Here are a couple different examples. You can see a little bit of divergence between the Modelica model and Hobart reed theory, and we attribute this to, again, the different formulations. However, what we also see is that we're also reducing some of the conservatism that's introduced in Hobart reed theory as we're getting closer to the experimental results. So in conclusion, I presented some details and examples for Roto-Aerolib. This can be used for a wide range of different studies for looking at the different effects of rotorcraft and all the complex multi-physics that go on, especially for the emerging electric vehicles that a lot of people are looking at right now. The library is available on GitHub. One note is that the development was done in Open Modelica, so if you happen to use another tool, it'd be much appreciated if you tried it out and reported bugs and gave suggestions. So with that, thank you for attending. If you have any questions on this presentation, feel free to contact me, and I would be happy to answer anything you have. Thank you for attending.